All right, in this video, we're going to talk about section 1.4, dealing with complex numbers. And in this video, or in this section rather, we'll talk about how to add and subtract complex numbers, multiply complex numbers, divide complex numbers, and perform operations with square roots of negative numbers. Okay, so the first thing we need to look at is the imaginary unit I, because that's part of what complex numbers are. The imaginary unit is going to be the lowercase I, and that's going to be defined as I is equal to the square root of -1, where I squared is equal to -1. Okay. So using the imaginary unit I, we can express the square root of any negative number as a real multiple of I. Now before, if you were to take the square root of a negative number and you try to do that in the calculator, you would get some type of an error message, because on the calculator, you cannot take the square root of a negative number and have it give you as an answer a real number. Okay, but with the imaginary unit, you are allowed to take the square root of a negative number, like the square root of -25. Well, that negative sign means that there is -1 in it. So I can break up the square root of -25 as this: the square root of -1 times the square root of 25. And by this definition of the imaginary unit, where I is equal to the square root of -1, if I take the square root of -1, I would get I, and that would be multiplied by the square root of 25. And I can find the square root of 25. That's going to be 5. So the square root of -25 will be 5i. Okay. So that's how we find the square root of a negative number. And we can write it as a complex number, which is the next thing that we will talk about. Complex numbers, along with imaginary numbers. The set of all real numbers in the form of a plus bi, with real numbers a and b, and I being the imaginary unit, is called the set of complex numbers. And in this case, the a is the real part. The b, that's going to be the number in front of the I, is the imaginary part. Okay. So if I had something like, let's say 7 plus 4i, that's an example of a complex number because it is in what we call standard form, a plus bi. Okay, a plus bi is what we call standard form. And if it's in standard form, we can identify the real and the imaginary part. That 7 is the real part. And the 4, that's the number in front of the I, is the imaginary part. Okay. Now, if b is not equal to 0, then the complex number is an imaginary number. An imaginary number is going to be in the form of bi, called a pure imaginary number. That means for a pure imaginary number, it's going to be something like this. The 5i that we use in this example, that would be a pure imaginary number because of the fact that I don't have a real part. All I have is just the imaginary part. So it's a pure imaginary number. Also, a complex number is said to be simplified if it is expressed in the standard form of a plus bi. Now, if b is a radical, then we usually write the I before the b. In other words, if we have something like 7 plus 3i, times the square root of 5, it would be best to put the I in front of the radical as opposed to putting it behind it, because people could get confused on whether that I is underneath a radical or is not. So to avoid that, we'll put the I in front of the radical. Okay. All right. Next, we'll look at equality of complex numbers. Expressed in standard form, two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So if I have a plus bi, and if it's equal to c plus di, that's going to be true if and only if your a, the real part, is equal to the real part here, c. A and c are your real parts, they have to be equal. B and D, which are your imaginary parts, they have to be equal as well. Okay. All right, next we'll look at operations with complex numbers, starting with adding and subtracting complex numbers. Okay. So number one states, if I have a plus bi plus c plus di, that means I can add the real parts together, a plus c, and the imaginary parts together, b plus d, with the I. So that's simply like combining like terms if you're dealing with variables here. So here we add the complex numbers by adding the real parts, adding the imaginary parts, and expressing the sum as a complex number. Okay, now for a plus bi and then minus c plus di, we subtract the real parts, a minus c, and then the imaginary parts, b minus d, and then we add the I behind it. Okay, subtracting the real parts, subtracting the imaginary parts, and expressing the difference as a complex number. Okay, like in parts A and B of this example. And we're going to do a few of these. Like 7 plus 2i plus 1 minus 4i. And the way we do that, we have the real parts, we'll add the real parts together, 7 plus 1 plus the imaginary parts are going to be 2i minus 4i. Or you can think of that as 2i plus negative 4i. So here I'm just combining like terms here, grouping the real parts and grouping the imaginary parts, and then simplify. 7 plus 1 will be 8 plus 2i minus 4i. In this case, that's going to be a negative 2i. Now, another way of writing 8 plus negative 2i would be this 8 minus 2i as the final answer. Okay. All right, now part B, we got 3i plus 2i minus 5i minus 7i. Or I should say minus the quantity 5i minus 7i. They're in parentheses. So this is a subtraction. That means I'm going to subtract the real part, which is 3 minus 5. And then I'm going to say plus, by the way. Subtract the imaginary part, 2i minus a negative 7i. Okay. So in this case here, if I do 3 minus 5, that's negative 2. Plus 2i minus 7i. Keep in mind, when I subtract the negative, that's the same as adding the positive. So this is like 2i plus 7i, which is going to end up being 9i. Now, now, if you wanted to, I'm going to do this in another color. If you wanted to, you could have did this. Bring down the 3 plus 2i without the parentheses, and that minus sign, change the sign of each term in the parentheses to the opposite. So the minus sign makes the 5 minus 5. The minus sign makes the minus 7i plus 7i. And then combine your like terms. 3 minus 5 is negative 2. 2i plus 7i would be plus 9i. Okay, so that's another way you could have solved that particular problem there. Okay, there's a couple more of these. 5 minus 2i plus 3 plus 3i. So here we're going to add or subtract as needed. Now you could have did it the way that I did in that first example, or just do this. Write this out without the parentheses. The plus sign is going to keep the 3 plus 3i the same way. And then combine your like terms. 5 plus 3, that's 8. And then 2i minus 3i, well, not minus 2i plus 3i. Negative 2 plus 3, that's going to be a 1i. Or just simply put 8 plus I. And I do need to warn you, in the homework, you have to write this in standard form, where the real part is first and the imaginary part is second. So if you enter it another way, they're going to mark it wrong. So make sure the real part is entered first, and then the imaginary part is entered afterwards in my math lab. Okay, let's try this one. 2 plus 6i, and that should be minus. 2 plus 6i, let's change that to a minus because we're supposed to subtract here. 2 plus 6i minus 12 minus I. So in this case here, I'm going to write the 2 plus 6i. This minus sign will make the 12 minus 12, and the minus sign makes the minus I plus I. And now we can combine like terms here. 2 minus 12, that's negative 10. 6i plus I. Well, 6i plus a 1i would give me a plus 7i. So negative 10 plus 7i would be the answer to that, to part B. Okay. All right. Next, we'll talk about multiplying complex numbers. Multiplication of complex numbers is performed the same way as multiplication of polynomials using the distributive property and using the FOIL method. That's first, outer, inner, and last when you're multiplying two binomials. Now, there is one thing that you do need to know, and that's this. We replace any occurrences of I squared with -1. So any occurrences of I squared, you replace it with -1. And the reason for that is the definition of our imaginary unit. It's defined as I is equal to the square root of -1, where I squared equals -1. So any occurrences of I squared, you're going to substitute it with -1. Like in this example, 6i times the quantity 7 minus 3i. All right. So here we're going to use our distributive property here because we have a pure imaginary number multiplied by a complex number. So in this case, we do 6i times 7, which means 6 times 7 would be 42, and then we bring over the I, and then minus 6i times 3i. Well, 6 times 3 is 18, and then I times I is I squared. Now here we have an I squared, so that means we need to substitute that I squared with -1. So I have 42i minus 18 times that I squared will be substituted with -1. And then we simplify. Let's see, 42i, bring that down, minus 18 times the -1 would be plus 18. Now we have to write this in standard form. That means we need to put the 18 in front, the real part, and then the imaginary part. So this will be 18 plus 42i. Okay. Now part B is the 7 minus 5i times -2i minus 3i. So here we have a pair of complex numbers. That means I need to use what they call the FOIL method. And that's, of course, for first, outer, inner, and last, if you're not familiar with the first FOIL method. So here it is. First term, 7 times -2. That's -14. Outer is this, 7 times minus 3i. That's going to be a minus 7 times 3, that's 21, bring over the I. Your inner, -5i times -2. Well, negative times a negative will be a plus. 5i times 2 would be 10i. And then last times the last. 5i times, well, minus 5i times a minus 3i. Well, negative times a negative is a plus. 5 times 3 is 15, and I times I is I squared. Okay. Now let's simplify this. I do have an I squared. I'm going to replace that I squared with -1. So let's bring down -14. And I'm going to combine these two like terms here. Minus 21i and a plus 10i will be a minus 11i. And then plus 15 times, substituting the I squared with -1. Because again, we replace any occurrences of I squared with -1. And that -1 times that plus 15 will be minus 15. So I have -14 minus 11i minus 15. And then -14 minus 15 will be -29 minus 11i. Okay. Okay, here's a couple more of these similar to the ones that I just did. Here we're going to find the products. And of course, replace our I squared with -1. And again, if you want to stop the tape and try to stop the video and try to do those problems, you're free to do so, and then come back to see to compare your answers. Okay. So in part A, you got 7i times the quantity 2 minus 9i. So we got a pure imaginary number times a complex number. So we need to use the distributive property by doing 7i times 2. That's going to be 14i. And then 7i times minus 9i will be a minus 63i squared. That's 7 times 9, that's 63. And then you have I times I, that's I squared. And we replace the I squared with -1. So I have 14i minus 63 times, substitute the I squared with -1. And then -1 times that minus 63 will be a plus 63. So I have 14i plus 63. Now, if you were to enter this in my math lab, they would count that wrong because it's not written in standard form. Standard form means that the real part is in front, that's the 63, and then the imaginary part is behind it, the plus 14i. So your final answer there should be 63 plus 14i. That's the answer that they want because it's got to be in standard form. Now, part B, we got 5 plus 4i times 6 minus 7i. We got two complex numbers in standard form. We're multiplying them. We need to use the FOIL method. So here's the FOIL method here. First times first, 5 times 6. That's 30. The outer, 5 times a minus 6i. That's going to be a minus 35i. The inside, 4i times 6 would be a plus 24i. And then last times the last term, 4i times a minus 7i. That would be minus 28i squared. Now, let's simplify this a bit. I'm going to bring down the 30, and I'm going to do negative 35i plus 24i. Combine those, I'm going to get a minus 11i. And then substitute I squared with negative 1. And that negative 1 will make the minus 28 a plus 28. So I'm going to have 30 minus 11i plus 28. And if I add 30 and 28 together, that's going to be 58. So I have 58 minus 11i. That's the final answer. Okay. All right, so far we talked about how to add and subtract and multiply complex numbers. Let's look at dividing complex numbers. Now we're going to have to use something called complex conjugates, because dividing complex numbers is not as straightforward as adding, subtracting, and multiplying complex numbers. We need to use, for this operation of division, complex conjugates. Here, the complex conjugate of the number a plus bi is a minus bi. Notice that the terms are the same. The only difference here is we switch the operational symbols from a plus to a minus. And if you have the conjugate of a and the complex conjugate of a minus bi, that will be a plus bi. Okay, so you're just switching the operational symbols. Now, if we multiply complex conjugates, we're going to get a real number. So like in this case here, a plus bi times a minus bi, that's simply going to be a squared plus b squared. Also, a minus bi times a plus bi. If you just use the commutative property, you're still going to get a plus b squared. A squared plus b squared, I should say. And to prove that, let's do this. A plus bi times a minus bi. If we use the FOIL method, that's the first term times the first term, a times a, that's a squared. The outer, a times a minus bi, would just be a bi, and it's going to be minus a bi. The inner, bi times a, would be a plus a bi. Just putting the terms in alphabetical order. And then bi times minus bi. That would be a minus. B times b is b squared. I times I is I squared. And of course, we substitute the I squared with negative 1. So I'm going to bring down the a squared. Notice negative abi and plus abi. If I combine those, they add to 0. And then bring down the minus b squared. Substitute your I squared with negative 1. And negative 1 times the minus b squared would be a plus b squared. So you're going to end up with a squared plus b squared. Okay. So here I'm just using a FOIL method just to show you that you'll get this. And you can do the same thing with a minus bi times a plus bi. You'll still get that using a FOIL method. Complex conjugates are used to divide complex numbers. By multiplying the numerator and the denominator, you will obtain a real number in the denominator. So here you're going to be multiplying the numerator and the denominator by its complex conjugate of that denominator. Like in this example. So let's say I want to divide and express the result in standard form. In this case here, we got 3 minus 4i divided by 4 plus 3i. And I'll go ahead and write this out. 3 minus 4i divided by 4 plus 3i. All right. Now let's look at our denominator in this case here. 4 plus 3i. We need the conjugate of 4 plus 3i. Well, the conjugate of 4 plus 3i is, we just switch the sign from a plus to a minus, so it'll just be 4 minus 3i. That would be the conjugate. So that means I'm going to multiply the numerator and the denominator by its complex conjugate, which is 4 minus 3i. So the numerator will be 4 minus 3i. The denominator will be 4 minus 3i. Okay, because you have to have opposite signs in between those two terms in complex numbers. That way you'll get a real number in the denominator. Now, let's simplify. In this case here, I'm going to put these in parentheses. In the numerator, you're going to have to use the FOR method, okay? You have to use the FOR method. So in this case here, the first term times the first term, 3 times 4, that's equal to 12. The outer will be 3 times a minus 3i. 3 times a minus 3i will be a minus 9i. Your inner minus 4i times 4. That would be a minus 16i. And then finally 4i minus 4i times a minus 3i. Well, negative times a negative, that's going to be a plus. 4 times 3 is 12, and I times I is I squared. And that's going to be divided by, now notice the denominator is going to be complex conjugate, so we're going to be using the rule of this, squaring the first term plus the square of the last term, or the imaginary part. Square the real part plus the square of the imaginary part. This is your A, the real part. This is your B, the imaginary part. So if I square the A, or square the 4, that's 4 times 4, that's 16. And this will be plus, because the I squared, which is negative 1, will make the minus a plus anyway. B is 3. If we square the 3 times 3, that'd be 9. So your denominator is 16 times 9. Now, if you wanted to, you can use the FOR method in the denominator. You're going to see that your two middle terms will add to 0. You'll be left with the first term and the last term squared for each one of them. Now, let's simplify this numerator. This I squared is negative 1. I'm putting the negative 1 there for I squared, because that's what it's equal to. Let's simplify that numerator. Bring down the 12. Negative 9i minus 16i will be a minus 25i. Since I squared is negative 1, that negative 1 will make the plus 12 minus 12. I'll divide it by 16 plus 9, that's 25. And notice 12 minus 12 ends up being 0, so that's gone. I will be left with negative 25i divided by 25. And of course, the 25s divide out. I'm left with a negative and an I. So my final answer there would just simply be negative I. Okay. All right, here's another example. Say it has something like this. Divide and express the result in standard form, like 5 plus 4i divided by 4 minus I. All right, let's look at our denominator, which is 4 minus I. Here I need the complex conjugate of 4 minus I. I'm just going to say the conjugate of 4 minus I, which is simply 4 plus I. All I do there is just change from subtraction to addition. The terms stay the same, but it's just the operational symbol that switches. So 4 minus I, its conjugate would be 4 plus I. So that means I'm going to multiply the numerator and the denominator by its complex conjugate, which is 4 plus I. And now we're going to multiply the numerator using the FOIL method. So in the numerator, I got 5 times 4. That's the first term times the first term. That's 20. The outer 5 times I would be a plus 5i. The inside, 4i times 4 will be a plus 16i. And then 4i times I. Well, 4 times 1 would be 4, and I times I is I squared. That would be divided by, now this is your A. The B is the understood 1 that's in front of the I. So I'm going to square the A plus the square of the B. A is 4. 4 squared would be 16. And the I has an understood 1 in it. I'm going to see if I can try to put that in there. There's an understood 1 there. So your B is going to be 1. 1 squared will be 1, and it will be a plus 1. Not minus, because I squared will change that minus into a plus. Okay, so now let's combine like terms in the numerator. That I squared is negative 1, by the way. So I'm going to bring down 20 and add 5i plus 16i. That would be a plus 21i. Oops, not 2i, 21i. Okay, and that negative 1, since I squared is negative 1, that negative 1 will make the plus 4 minus 4 over 16 plus 1. That's 17. Now if I add 20, do 20 minus 4, that's 16 plus 21i all over 17. Now, let me warn you, if you try to enter this as your answer in my math lab, you will be counted wrong for that problem. It has to be in standard form, which means you're going to have to break this apart. Keep in mind the 16 is over 17, so that's 16 over 17 plus 21i is over 17. But you're going to have to write it like this, 21 over 17, and then the I will be next to it like this. Here that I can't be in the numerator or the denominator. So it just had to be off to the side where 21 over 17 is, if you had a problem like this in my math lab. Okay. All right, next we'll look at roots of complex numbers. Roots of negative numbers, roots of negative numbers. And we're going to talk about the principal square root of a negative number. For any positive real number called b, the principal square root of a negative number which is negative b, is going to be defined as this. The square root of negative b equals to I times the square root of b. And it's always going to be that because in negative b, there is a negative 1 in it. So I can break negative b underneath the radical as this, the square root of negative 1 times b. And the square root of negative 1 will be I, and the square root of b will just be square root of b. Now, when performing operations with square roots of negative numbers, you will always begin by expressing all square roots in terms of I. That will be the first thing you do. Express all of your square roots in terms of I, and then you will take your square roots. Okay, and I've also included here a table of perfect squares. If you're not familiar with your perfect squares, here they are in this handout from 1 to 10. Because you're not always going to find the square root in this table. You might have to use the largest perfect square that would go into a particular number. Like in this example here. Here we're going to perform the indicated operations and write the result in standard form. Here we got the square root of negative 48 minus the square root of negative 75. All right, in this case, the square root of negative 48, we need to first write these in terms of I. Okay, so in other words, we need to pull the I out from underneath the radical. So the square root of negative 48, where I can write that as I times the square root of positive 48 minus square root of negative 75. I can pull the I out. So it'll be minus I times the square root of 75. All right. Now, as you can see, underneath the radical, the 48 and the 75 are not perfect squares. You're not going to find them in this table. However, we can find the largest perfect square that can go into each one of these, like the square root of 48. I need to find the largest perfect square. Looking at this row for n squared, I need the largest perfect square that can go into 48 evenly. Well, I know 49 is too big. 36 can't go into 48. 25 can't go into 48, but 16 can. Let's use that. Because 16 goes into 48 3 times. So I'm going to use 16 as the largest perfect square. So this is I times the square root of 16 times 3. Because 16 times 3 is 48. And then minus I times, well, 75 is not a perfect square. I need the largest perfect square that goes into 75. Well, in this case, it looks like 25 will have to work because 25 goes into 75 3 times. So 75 can be written as 25 times 3. And then we can take the square root of our perfect squares. That's the square root of 16 and the square root of 25. We can take the square root of those. The square root of 16 is 4. So the 4 will go on the outside of the radical. So I have 4i. That square root of 3, that 3 has to stay underneath it. Because 3, of course, is not a perfect square. And then minus, take the square root of 25. Well, that's going to be 5. So the 5 goes out in front of the I times square root of 3. Now notice we have like terms here. I square root of 3, I square root of 3. So we can subtract our numerical coefficients. 4 minus 5 will end up being negative 1. So I'm going to have negative 1 times I square root of 3. But I can, of course, do without that 1. because it's understood to be a 1 in front, I can write it as I, negative I, square root of 3 as the final answer. Okay. All right, here's the next example. The quantity of negative 2 plus the square root of negative 7 squared. Well, to begin with, let's write this in terms of I first. So here, bring this negative 2 over, and then plus the negative underneath the radical, underneath the square root. The I has to come out. So it'll be I square root of 7, and that quantity will be squared. Now notice that this expression is used as a factor 2 times. That's where that exponent of 2 is. So I can write this out twice as negative 2 plus I square root of 7 times itself, negative 2 plus I square root of 7, and then use the FOIL method to multiply those two complex numbers. So the outer, negative 2 times negative 2, that's 4. Well, the first times the first, then the outer. Negative 2 times I square root of 7, that's going to be a minus 2I square root of 7. You can't multiply what's on the outside of the radical with numbers that are on the inside. Keep that in mind. Your inside, I square root of 7 times negative 2. That's going to be another 2I square root of 7. And then the last times the last. Well, I times I will be a plus I squared. The square root of 7 times itself will be the square root of 49. All right, now that I squared, of course, will be negative 1. So I'm going to put negative 1 right here because that's what I squared is equal to. Keep in mind, any occurrences of I squared, you substitute it with negative 1. So I'm going to bring down the 4. Combine these like terms. I squared root of 7 are like terms, so negative 2 minus 2 will be negative 4. So I have negative 4 times I square root of 7. And that I squared will be negative 1, but that's going to change that plus sign to a minus. The square root of 49, what number times itself gives you 49? Has to be 7. So I have 4 minus 4I square root of 7 minus 7. And then combine like terms here. 4 minus 7, negative 3. So I got negative 3 minus 4I square root of 7. Okay, here's another one of these. Negative 30 plus the square root of negative 72 divided by 3. Well, let's first write this in terms of I. So here, there's a negative sign underneath the square root. So I'm going to bring over negative 30 plus and take the I out in front. So the I square root of 72 divided by 3. All divided by 3, I should say. Now, I need the largest perfect square that can go into 72 evenly. Let's see. I'm just bringing this down so I can look at this table, and I see that 36 will be the largest perfect square that goes into 72 evenly. Okay, so I have negative 30 plus I square root of 36 times some number that gives me 72, has to be 2, all divided by 3. All right, so next will be negative 30 plus the square root of 36 is 6. So I can pull the 6 out in front of the I. The square root of 2, that 2 has to stay underneath that radical. That's going to be divided by 3. But in this case here, we can simplify this by taking negative 30 divided by 3 plus 6I square root of 2. That's divided by 3. Well, negative 30 divided by 3 is negative 10 plus 6 divided by 3 is going to be 2. So I have 2i square root of 2. So the final answer there will be negative 10 plus 2i square root of 2. Okay. Okay. And this is the last set of examples here in this video. Again, you can stop the video. Pause the video so you can get an idea how to do some of these problems here without before I give you the answer to them. But here, they're pretty much similar. All right, here we're going to perform the indicated operations and write the result in standard form. So here, square root of negative 27 plus the square root of negative 48. Okay. First of all, I need to express this in terms of I before I do the square root. Well, there's a negative. That means I comes out times the square root of 27 plus another negative here. The I comes out square root of 48. So I'm writing this in terms of I before I do anything else. So now, let's look at the square root of 27. It's not a perfect square, so I need the largest perfect square that goes into 27 evenly. And that's going to be 9. Because I know 9 goes into 27 3 times. So I'm writing the square root of 27, that's the square root of 9 times 3. Then plus I, square root of. I need the largest perfect square that goes into 48 evenly. That would have to be 16. That'd be 16 times 3. And I think I did a problem similar to that that has the square root of 48 in it. And now we can take the square root of the perfect squares. Like 9 is a perfect square. The square root of 9 would be 3. The 3 comes out with the I. And this other 3 stays underneath the radical. So it'll be 3i square root of 3 plus square root of 16. I can take that. That'd be 4. So it'd be 4i and square root of 3. Now we can combine like terms because we got I square root of 3 here and I square root of 3 here. So if I add 4 plus 3, that will give me 7. So I have 7i square root of 3. And that will be the final answer to that problem. Okay, part B. Negative 2 plus the square root of negative 3 quantity squared. Well, there is a negative here that I comes out. So that means I'm going to have negative 2 plus I square root of 3 quantity squared. Now I'm going to write negative 2 plus I square root of 3 twice because the exponent there tells me that this is used as a factor twice. So negative 2 plus I square root of 3, and that'd be multiplied by negative 2 plus I square root of 3. And then we use the FOIL method. So here, negative 2 times negative 2. First times first, that's 4. Outer, negative 2 times I square root of 3 will be minus 2 I square root of 3. Inside times the inside, I square root of 3 times negative 2 will be another negative 2I square root of 3. And then the last term times the last term, I square root of 3 times I square root of 3. This will be plus I times I is I squared. The square root of 3 times the square root of 3 will be the square root of 9. And of course, I squared is negative 1. Remember, you substitute all occurrences of I squared with negative 1. So I'm going to bring down the 4 here, combine these like terms here, because I got I square root of 3 and another I square root of 3. Minus 2 would be a minus 4 I square root of 3. Now, that negative 1, since it's Since I squared is equal to -1, that -1 will make the plus sign a minus. The square root of 9 is 3. And then combine the constants. 4 minus 3 is 1. So I have 1 minus 4i square root of 3. All right, that'll be the final answer. And finally, negative 14 plus the square root of -12, all divided by 2. Okay, there is a negative underneath the square root, so the I comes out. So it's negative 14 plus I square root of positive 12 over 2. Well, for the square root of 12, it's not a perfect square, so I need the largest perfect square that goes into 12. In this case, it'll have to be 4. So I'm going to bring negative 14 plus I times, rewrite the square root of 12 as the square root of 4 times 3, all over 2. And of course, the square root of 4 will be 2. So I have negative 14 plus the 2 comes out with the I, and then square root of 3, all over 2. Now, I'm going to break this up as negative 14 over 2 plus 2i square root of 3 over 2. And simplify each piece. Negative 14 divided by 2 is negative 7. Plus 2i square root of 3 divided by 2, but the 2's divide out. You'll be left with I square root of 3. If the 2's divide out, you're left with I square root of 3. So the final answer will be negative 7 plus I square root of 3. Okay. All right, so that concludes this video on section 1.4, dealing with complex numbers. So do feel free to email me if you have any questions about the homework for that section, or you have any questions about the problems that were discussed in this video.